Hello everyone, I'm Yingyi from iPads at Shanghai University. I'm honored today to present our work, first class ready for airdrops via grouped I/O API with transparent read-write optimizations. This is a joint work with Shanghai University and the Huawei Cloud. Our system AITURBO addresses an important problem in cloud AI workloads, how to scale storage bandwidth cost efficiently without requiring significant coding effort, enabling a large-scale airdrop to proceed smoothly. Let's start with some context. We are witnessing an explosion of AI applications, from conversational assistants to robots. These applications are powered by various foundation models. What's particularly important for us here is how these models interact with storage through their life cycle. During training, we need data size streaming and periodic model checkpoint for fault tolerance and model debugging. During inference, we need to load model weights and potentially offload QA cache to storage. Here, I'll use training checkpoint for tolerance as a showcase. Please refer to our paper for more cases if you're interested. Large training job periodically write checkpoints, which include model weights and optimizer states. This is necessary because failures are common at cluster scale. Even a single uncorrectable ECC error on one XPU can terminate the whole job. To avoid stopping computation, our system usually writes checkpoints to storage asynchronously, so training can continue while data is uploaded in the background. However, frequent checkpoints demands very high write throughput, otherwise storage stall computation and waste expensive XPU hours. For example, a 38B model needs about 86 gigabytes per second sustained storage bandwidth to completely hide checkpoint overhead at per iteration checkpoint per frequency. However, there are two key challenges to provide sufficient bandwidth from cloud storage. First, compute storage disaggregation limits effective bandwidth utilization. In modern AI clusters, each XPU connects through the high-speed compute fabric at around 200 gigabits per second and can be fully utilized this bandwidth for local computation. However, when these accelerators need to access cloud storage, they can only go through the storage fabric, which provides only about 12.5 gigabits per second per device. This lower fabric bandwidth limits the throughput the storage system can provide to the accelerators. Second, increasing storage bandwidth requires deploying more storage servers. To provide higher throughput, the system must add more storage nodes and network links. This directly increases infrastructure and monetary cost. So it's important to understand characteristics of AI jobs before optimizing cloud storage bandwidth. First, AI jobs often rely on asynchronous I/O, so computation and data transfer can overlap, as I showed previously. Second, AI training jobs typically involve bulk I/O, moving large amount of data at a time. And this can be seen in the CDF of I/O sizes. As you can see, the majority of I/Os are quite large, confirming that bulk transfers dominate AI workloads. Given these characteristics, the first principle of optimizing cloud storage is straightforward. We should reduce the payload, that is, minimize the amount of data that need to be transferred, and improve effective bandwidth available to the job. So, what are the design details of AITURBO to optimize storage bandwidth for AI jobs? First, let's dive into reducing I/O payload. Important observation is that AI jobs often have data redundancy. Data parallelism is prevalent in distributed training. When using data parallel, each compute node processes different data samples but maintains identical model states. Mathematically, the I/O time equals the model states times the replication factor divided by bandwidth. If we can eliminate this redundancy, we directly reduce I/O payload. So our goal is simple: identify and eliminate redundant I/O operations across compute nodes. However, deriving an optimized I/O plan for AI workloads is still challenging. First, different jobs exhibit diverse redundancy patterns and variations in training frameworks, parallelism strategies, and model types make it hard to reuse a single strategy. As shown in the table, different training parallelism strategies lead to different redundancy patterns. which further complicates I/O planning. Second, whenever an application uses a new or customized training framework, additional engineering effort is required to integrate it into with our I/O plan. OpenSora is such a case. We made two observations about AI workloads that motivate our approach. First, AI jobs work in a BSP fashion. That is, distributed training proceeds in synchronized iterations, and checkpoint I/O is performed across all nodes simultaneously. Second, redundancy metadata coordination is cheap. Checkpoints usually consist of a small number of large tensors, so metadata is tiny compared to the actual data. This combination of two observations enables a lightweight cross-node I/O coordination. Our group I/O API is inspired by collective communication libraries like Nico. Just as Algether synchronizes tensor operations across nodes, our group put file synchronize I/O operations. All compute nodes conduct a group of I/O operations together synchronously. This API is easy to understand and can be readily adopted by different applications, as it made almost no assumption about the training framework. So, how does the group I/O API work behind the scenes? Let me walk you through its three phases. First, we collect the I/O operation metadata from all compute nodes. Second, we derive an optimized I/O plan from a global view, deciding which node writes which data. Finally, we execute the actual storage I/O. In this example, we show one important optimization enabled by group I/O API, that is the deduplication. With cheap metadata coordination, group I/O API effectively reduces the replication factor, thus cutting overall I/O time. However, one challenge remains: how do we obtain redundancy metadata regardless of which training framework is being used, especially for our bleeding edge or legacy applications? Rather than parsing every format individually, we take a different approach. We transparently generate metadata from data itself using checksums. Global metadata gathering only begins once all XPUs have finished hashing their tensors. On the right, you can see an example of the duplication pattern detected through this checksum-based approach. To minimize checksum overhead, we use Big 3, a parallel-friendly hashed algorithm with XPU acceleration. Moreover, metadata can be cached across iterations to further reduce overhead. Another common concern here with checksum-based deduplication is hash collision. Thankfully, with Blake 3's 256-bit output, the collision probability is cryptographically negligible. This means we can safely identify duplicates without any knowledge of the framework's internal formats. Now, let's move on to the next part, how we improve available I/O bandwidth. There are two important facts about modern general-purpose AI clusters. First, host DRAM is often underutilized to support memory-heavy workloads such as the recommendation models. The AI cluster are provisioned with large amounts of host DRAM. However, when other types of training jobs are scheduled, a significant portion of the host DRAM remains idle. Second, the compute fabric provides significantly higher bandwidth than the storage fabric. Compute nodes are typically connected through high-speed interconnects, offering very high per XPU bandwidth. In contrast, storage fabric generally provides a much lower bandwidth per XPU. Following prior work, we designed our system to exploit the compute fabric and host DRAM as a fast storage layer. Instead of treating DRAM as a RAID buffer, we treat it as a storage tier itself. Checkpoints are written directly into distributed host memory across compute nodes interconnected by high-speed bandwidth compute fabric. Flushing to remote storage is now optional and can be performed asynchronously at a much lower frequency to match the available class storage bandwidth. Now, A natural concern here is durability because host DRAM is volatile. First, training workloads are inherently tolerant to data loss. If a node-level failure occurs, we can roll back to the loss value checkpoint in cloud storage and recompute the missing iterations. Second, to minimize data loss and recomputation, following prior work, we also replicate checkpoint data across multiple nodes. However, turning host DRAM into storage is not automatically fast. To actually achieve high bandwidth, we need careful I/O planning. In the future architecture, I/O is no longer a simple write to a storage server. Instead, it becomes many-to-many data movement across heterogeneous components, such as XPUs, host DRAM, SSDs, and cloud storage. First, we must respect the hardware topology. Different links like PCIe and the NICs have different bandwidths. If data placement ignores topology, certainly quickly become bottleneck while others remain underutilized. Second, we need load balancing. Because DRAM is distributed across nodes, naive placement could create hotspot nodes or congested network passes, limiting the aggregate bandwidth. Finally, we also need to perform replication for fault tolerance, which introduces additional transfers that must be coordinated carefully to avoid wasting bandwidth. So the problem is essentially deciding where data should go, how it should be replicated across sources like XPUs and destinations such as DRAM, SSDs, and cloud storage. To address this challenge, we designed an automatic I/O plan generator. Given the cluster topology and bandwidth constraints, the generator computes an optimized I/O plan that determines where each piece of data is written to maximize aggregate bandwidth. We formulate this as a bilinear program. The objective is to minimize the end-to-end I/O completion time, denoted as T. The decision variable is transfer rate from a source node I to a destination J for each tensor K. In other words, we are determining how each node should use its bandwidth to send different tensors to different destinations. And this optimization is subject to several constraints. For example, we must satisfy the required replication factor for fault tolerance, and both source and destination nodes cannot exceed their hardware bandwidth limits. However, solving a bilinear program directly is too slow in practice, so we introduce some approximation. Instead of solving T and the transfer rate together, we bandwidth search the minimal feasible I/O time within a target precision. For a fixed T, we only need to check whether a valid bandwidth allocation exists. This reduces the problem to a linear program feasibility check, which is much cheaper. We can further simplify the problem in two ways. First, we can group multiple tensors into larger I/O units, reducing the number of individual operations. Second, XPUs on the same nodes can be merged into a single logical source, since they typically perform similar I/O operations and share the same hardware configurations. With this optimization, the plan can be computed in seconds to minutes for an 8-node cluster. Second, the training is iterative, so checkpoint patterns are stable. We can cache and reuse the generated I/O plan, making the planning overhead negligible. Finally, for some cases, we can also use heuristics instead of solving the optimal plan. Next, I'll show you our evaluation results. For our evaluation, we tested a variety of AI storage workloads. Here, we focus mainly on checkpoint writes. Results for other workloads are available in the paper. Our hardware setup consists of 64 ASCEND 910B NPUs allocated from Huawei Cloud, connected via 200 gigabits per second compute fabric and 100 gigabits per second storage fabric. We evaluated our models for different sizes from 1.5B to 38B and tested both with and without zero optimization. For end-to-end checkpoint performance, we compared AITURBO against Megatron and Gemini. AITURBO achieves significantly lower checkpoint time. Megatron includes deduplication in the evaluated commit, but it does not leverage host DRAM or the compute fabric at the fast storage layer to alleviate cloud storage bandwidth bottlenecks. Gemini, on the other hand, writes checkpoints to derive over the compute fabric, avoiding cloud storage overhead, but it does not perform deduplication or generate an optimized write plan like AITURBO. We also measured visited execute time as the optimal checkpoint frequency, following the formula from prior work. AITURBO reduces visited execute time compared to both baselines, demonstrating its efficiency in practice. A factor analysis shows step-by-step improvements. Adding host DRAM gives a baseline boost, checksum-based deduplication, and the optimized write plan further reduce checkpoint overhead. To conclude, our work shows that the storage bandwidth demands of AI jobs can be scaled cost-efficiently with minimal coding effort. This is achieved through a holistic design combining three key elements: a grouped I/O API, the compute storage fusion architecture, and an automatic I/O plan optimization. AITURBO has been used to accelerate checkpoint writing in Huawei's production environment. Thank you all for your attention. I'm happy to take any questions.